推动的，你知道吗？所以就是说，现在是算是但是特别难放，然后呢，有人就想说，桌子右小兵，然后这个不仅高级，然后每一个往前这样的方向就然后然后这个打出来之后，然后就在这里打出之后。
All right. Good afternoon, everyone. So let's get started with lecture today. But before, I have here Kieran. Kieran is one of your tutors, and he is marking our assignment number 1. So blame him. And he has an announcement to make. So before we get started, let's just hear him.
Yeah. All right, so as you know, you might already know me, but if not, my name is Robert Kieran Chantrell. So I'm conducting research at the university and I'm looking for participants to join the study that I'm doing. So I'm just going to begin by asking, have you ever been frustrated trying to install a software package? Maybe you don't know what a software package is anyway. But you might imagine, even if you haven't, that software packages can frequently be awkward to install. You can suffer from dependency issues, compatibility issues, and really difficult to follow instructions. So the motivation of this study is to find the factors of software packages and developers which influence the software installation experience. So as a participant, you would be required to conduct a 15-minute questionnaire, as well as attend a 1 hour and 15-minute session 4 times, where once you'll be asked to install a software package under observation for a period of 1 hour, and also a follow-up 15-minute interview. You'll be compensated as well, $50 for your time at the completion of the study. And as well as that, I'm also looking for observers. So if you're looking to volunteer, it's a great way to get involved and get first-hand research methods experience in an actual study. So yeah, if you're looking for that, it's certainly a good opportunity as well. So if you're interested in either being a participant for the study or being an observer, please send me an email at robert.chantrell@student.adelaide.edu.au. Your contribution will help us to achieve a software installation framework which might make it easier to install software in the future. So thank you for your consideration, and I sincerely hope you sign up.
All right, thank you. So, I mean, one thing that is important to say is that even though you are first years, if you are interested in research, it's really good to get involved right away, okay? So don't wait until you are a second or third year. If you're interested in research, just, go and start working on that. All right. So we're going to start a new topic today about mathematical principles, and first lecture is going to be on invariance. So invariance is a very tough topic, so you may be frustrated at some point today, but I mean it's a very important topic, and we will go through several different types of invariance. Before I get started, so last chance for questions on assignment number 2. Yes? Definitely. Don't give me the proper answer. I mean, just the equation. You cannot write the proper answer, yeah? So any other questions? All right, so assignment number 3 will be out today. I will try to put this as early as possible. If for some reason I get delayed on this, just email me. It's already ready to go, but sometimes a lot of things come up and then I forget. So, but tomorrow you will have assignment number 3. Okay. All right, so let's get started with today's lecture with this piece of history, but it's not very clear if this is actual history, but the kind of it gives you an idea of who Gauss is. So do you know who Gauss was actually? Gauss was probably one of the most intelligent, smart guys on this planet, and he has so many contributions. It's really hard to tell, everything that he's done. But let's just focus on this little part of his life. So he was 9, and there was a lazy teacher who gave him not him, to the whole class, some exercise, which was supposed to be very hard. And the exercise was, just to sum all integer numbers from 1 to 100. So, of course, teacher did that so he could just go out and do whatever. And Gauss got the answer very quickly. Of course, if you try to sum all the numbers by hand, it will take you a long time. But Gauss figured out something that is very clever, considering that he was 9 years old. So let me try here to see, to show what he did. So he was just doing what the teacher told him to do. And then let's go like this. Okay, so then he probably realized, right? So if I keep summing this, it's going to take forever. But there's one pattern that he discovered, which is, again, everyone knows, right? So if you probably know this formula, right? So if you have I equals 1 to 100, so let's put n because it's usually the letter that you use. This is equal to what? So what is this formula? Come on, you should know this. Yes?
100 times by 101 divided by 2.
Yeah, so it's going to be 100 times 101 divided by 2. Actually, this is not what I want to do. But, in general, if you take the sum of I equals 1 to n, this is going to be equal to, in general.
N times by n plus 1 divided by 2.
Cool. All right. Okay. So how did Gauss figure that out?
He went 1 plus 100 is 101.
Yes.
2 plus 99 is
Exactly. So that's exactly the pattern. So there is a big invariant here, which is if you look at the numbers on the ends, if you sum them, you're going to have 101. So take 2 and 99, again 101. So that's the invariant. So there's this invariant of 101, and that thing here repeats 50 times, which is, 100 divided by 2. So that's the formula. Just put 100 here, 101 here, and then the 50 times here, and that's it. Very, very clever. And so today we're going to kind of work on different problems along the same lines, right? So trying to find these invariants. Mathematically, these are amongst the hardest problems, but you get a real rush when you find the answers for these questions, okay? So let's try to get some of these questions done today. Okay, so this one, I'll let you work on a couple of minutes, okay, on this. So tennis tournament. So there's a tournament with 937 players. The player who wins the game advances. The loser leaves the competition. How many games are required to complete the tournament? So try to work. If you know the answer, just, hold on a bit. But try to work on this, and then we will try to solve this together.
would have a third place match.
No, no, loser goes away. There's no third place match. But the answer is easy. Answer is easy.
Yeah.
Hmm?
I thought we did something like this earlier. In like week 1 or something.
Probably. Today we're going to see a lot of similar cases. Next one will be similar too. It's way too loud.
10.
10. 10 games.
11.
Comparing with a 2 to the power and 4 and A16, whatever it's bigger than 9300, 937 is the number.
So do you understand the question?
Right.
So you have a tennis tournament. So I play with you if I win, I advance. If I lose, I
It's a round. Okay.
yeah.
And for
There's no
the
round.
assignment here, I'm not quite sure if the answer is right. Can you verify? Just tell me right or wrong.
For what? For your assignment?
Yeah, the answer. Just tell me right or wrong.
After lecture, come talk to me.
Is it that?
Yes. So where is the invariant?
One person.
You get it? All right. So every time you see a question with weird numbers like 937, I mean, it looks suspicious right away, right? So, you know, it's not a common number, let's say, but, you know, just be suspicious, right? So, and the best thing to do sometimes is to either scale up or scale down the question. In this case, let's scale down the question. And other problems, we're going to see the next questions like this. You can also put numbers to the variable so that can help you solve the question. But, you know, with 937 players, maybe you say, okay, you know, this is too much. So let's try with 2 players instead. You know, with 2 players, so how many games are there? Just 1 game, right? So you have 1 game and 1 player. So, you know, after 1 game, you're going to have 1 player. So let's say, you know, 1 game, 1 player. So with 3 players, how many games do I need? 2, right? So 2 games to get to the final player, right? And, I mean, the pattern becomes quite obvious. So for 4 players, you're going to need 3 games to finish with 1 player. All right. So then what is the invariant? Yes?
Every game you knock out 1 player.
Well, that's not really the invariant.
Okay, so if you have any number of players, the number of games you need is 1 less.
Exactly. Yeah. So if you see here, 4 is going to be 3 plus 1. So the number of players left times the number of games played, that has to be equal to the number of initial players in your tournament, always. So for example, in this tournament with 4 players, let's say I don't tell you anything, right? So if I say, you know, there has been 2 games played in this tournament with 4 players, how many players are left? 2, right? So because number of games plus number of players has to be equal 4. So that's the invariant. Number of games plus number of remaining players has to be equal to the number of total players. All right, so any questions here? Cool. So let's move on to a more interesting question, which is a question that I presented earlier. So this one I will give you some more time to solve. It's a bit trickier. So this is, I think I presented this in the first class, but now we're going to solve it more properly. All right. So you have a glass of juice and a glass of water. They have exactly the same volume. And then you have a spoon. So you take 1 spoonful of juice and put it in the glass of water. And then you mix up the glass of water with the orange juice. Take another spoonful of this mixture and put back to the orange juice glass. The orange juice glass initially had pure orange juice, so whatever that means, there's no water, but, let's say it's pure orange juice, and the other one has pure water. And after one exchange of the spoon, from 1 to 2 and then back to from 2 to 1, what amount is greater? The amount of water in the juice or amount of juice in the water? All right, so try to work on this. I will keep giving hints along the way, but it's important that you try to work on this question. Yes.
It's equal, right?
It is equal, yeah. But how do you solve this?
Because you move a spoonful of juice into the water. There's equivalent of 1, and then when you mix it, and you take a spoonful from the water, the amount of juice and water comparative is equal. Like the ratio is equal in the spoon as there is in the glass. You move that back over, then the ratio is inverted in the juice, and it's the same volume in both, theoretically.
Okay.
So it's just, you've got the same ratio. Yeah.
It is
It's
the same.
a bit of a wide leap of logic, but that's how I got it.
But I actually wanted to see, like on paper. And
We're just wrestling down.
Huh?
We're just wrestling down. Did you want us to wrestling down?
Yeah.
So I just gave an example. Take 20 of juice to the water. So the water will be 120. So take 12 to from 120 to the 8. So we'll be the
Yeah.
So the water in the juice, right?
This is the amount of.
I think if this water, it will be water. If this juice, it will be juice.
Just the same, right? Or not?
Not same.
Not the same?
Yeah.
So work a bit more. Oh, let. It is.
Just, so you want to say now juice or water are same?
I mean, in the end,
The water in the
yes.
juice, the juice in the water.
It should be the same, yeah.
Because it doesn't matter if it's water or juice.
Yes, yeah,
It doesn't matter if it's water or juice.
yeah. Did you get the same? I'm not sure if you did.
Yeah, because if it's water, it will be juice. If it's juice, it will be
Yeah,
water.
yeah,
It's same.
yeah, yeah. Okay, so remember what we've been discussing, right, about the rules. So the first thing you need to identify are your variables. In this case, you're gonna have two variables, V, which is the volume, let's call it the volume of each one of these glasses. They are the same for the two glasses. And the volume of a spoon, which is X. So let's just call it X. So now the question is, you have this first move, which is, you take a spoonful of orange juice and put that into the water, which means that now you're going to have an X. So, glass one will have, the water glass will have X volume, X liter, let's say, of orange juice, and it still has V of water, right? And so after you mix that up, and put this spoonful here into the mixture and grab the mixture back to here, how much of water and how much of orange juice is in this spoon? So that's kind of the main question that you need to answer. So water glass at this point has X orange juice, V of water. You mix that up, and then you take another spoonful here from the mixture, and then the question is how much orange juice and how much water is in this spoon? If you think it's hard to work with variables, usually a good idea is to put numbers here. So let's say, here the volume is 100, and here X, the volume is 10, for example. So you can also do this. That sometimes helps you. So either way should be fine, okay?
Can I do it this way? So say that I represented it using numbers, no, not numbers, circles. The circles is orange and the squares is water. So in the first exchange, you got two circles and you got three water, one circle. So B is now 25% juice. And on the second exchange, because we're bringing back the whole amount, so we've got 3/4 of water times by a third, because there's 3 of those, because we're bringing back the circle now.
Yes.
So this is times together, so it's 1/4
That's perfect, yeah.
water, and that's
That's
1/4
good, yeah.
juice still.
That's good.
So I'm allowed to do it using that way.
Yeah, yeah. That's good. Yeah.
Mathematical way of showing it.
Okay.
Okay. B1 is like the cup, the cup with orange juice in it, but like after. B2 is the cup with water, but after. So that's B1, and then that's like juice and like water.
Yeah, that's a lot easier. Cool. That's good. That's easier than this one.
Yeah.
Yes.
So yeah, we're having using the same method, but I'm like setting the 10A and B, and I set the this volume of the spoon is 4, and but like a spoon is like 6B for the juice, and then 10A and 4B, and then there's like mix it up, so there's like a possibility. the
Yes.
value ratio for the
The
form.
ratio, yeah, not the
And then
probability.
just minus the thing out.
Yeah.
Yeah. Okay.
So what is the result?
Result, I think I gave it a little problem, but there's more A. There's more B in A than more A in B.
So then it's wrong.
Oh. It's calculation.
All right. You know, to understand like the proportion of water, I mean the amount of water and orange juice in the spoon, you know, in the second move, when you take the spoonful from the mixture back to the orange juice, we need to compute like the proportion of, let's say, orange juice in this water glass, not the, you know, the ratio essentially, which will be x divided by x plus v, right? So, you know, the whole volume will be x plus v, and the amount of orange juice will be x. So this is important because that's going to be the ratio of orange juice that will be in this spoon. Because, you know, it's a perfect mixture, right? But that ratio, of course, has to be multiplied by the volume that the spoon can take, which is x, right? So that's the volume of the spoon. So the amount of orange juice in this spoon going back is going to be x times x divided by x plus v, right? Which is this ratio of orange juice in the water. So this is the amount of orange juice in the spoon coming back to the orange juice. Okay? So the question now is, what is the amount of water in this spoon? I'm going through a very long way to solve this question. There are much easier ways, but I just want to go through the long way so you can see how easy the question actually is. This is the first one. It's going to be a bit hard. But so this is the amount of orange juice in the spoon. So the question is, what is the amount of water in the spoon? Yes? Yes. So amount of water is going to be x minus x times x divided x plus v. So that's the amount of water in the spoon. Now it should be clear. So what is the amount of orange juice that remained in the water glass? That's the amount of orange juice in the water. So we already know the amount of water in the spoon that will go to the orange juice. But we want to see what is the amount of orange juice that stayed in the orange juice glass. Yes?
X take what you took out.
Exactly. Because, you know, this is the amount of orange juice going back here. So the amount of orange juice that remained there is going to be x take x times x plus v. So this is the amount of orange juice in a glass of water. So you can see that these two amounts here are exactly the same. It doesn't change. So, okay, so this is a very convoluted way to tell that this is the same. I mean, a much easier way is if we imagine that the amount of, you know, the volume of the spoon is going to be water plus juice, you know, on the way back. You know that this is true, right? So forget about all these calculations. Let's just focus on this. The amount of, well, the volume of the spoon will take the volume of water plus the amount of juice. And you don't care what they are. You know that there is going to be water and juice because that comes from the mixture going back. So then you know that the amount of water in the orange juice is going to be W. And what is the amount of juice that was left in the glass of water? It's going to be the amount, the volume that you have here, minus the amount of juice that is in there, right? So that's going to be the amount of juice that remains in the glass of water, which is going to be x minus j. So this is the amount of water in the orange juice, And this is going to be the amount of orange juice in the water. So what is x minus j? Come on, help me. So if you look at this question here, so if you look at this formula, x equals w plus j. So if you take x, take j, that's going to be the same as water. All right? Does that make sense? I mean, am I saying something that doesn't make sense? Do you have questions? All right. But I haven't told you what the invariant is. So what is the invariant? So if you look at both glasses, they have water, let's say water, and they have orange juice. Whatever mixture you do, whatever exchange you do, what's going to be the invariant? Both of the glasses will have volume V. It doesn't change. So whatever you take from here and move there, that's going to be the amount of water that's left in here. So that's the invariant. So whatever exchange you make, it will never change. So the amount of water in the orange juice will always be the same as the amount of juice in the water glass. Is that good? Yeah. Cool. Okay. Any questions? All right. Sorry. Okay, sorry, the PowerPoint keeps crashing on me, so let's move on with. All right, so this is kind of the image that you should have in mind. This is the invariant of this puzzle. Let's move on to another one, which is, I think it's a bit easier than this one, but again, there is an invariant. So you have this rectangular chocolate bar consisting of m times n rectangles, and you wish to break it into its small blocks. At each step, you can only pick one piece and break it along any of its verticals or horizontal lines. How should you break the chocolate bar using the minimum number of steps? So, and you cannot stack them together and break all at the same time. So you have to just break one by one, right? So what is the invariant here? Yes.
You always break one piece whenever you break it.
So how did you achieve this solution?
So you just sell the whole chocolate bar, you spin it, you get two pieces of chocolate bar. Take one of these, spin it, you get three.
Yeah.
So every time you break one piece.
Right. So again, if the question, if you look at this bar and it's too big, one thing you can always do, imagine a chocolate bar with two pieces. So with two pieces, you have to break it once. And then 3 pieces. With 3 pieces, you have to break it twice. So it's always going to be, m times n take 1, no matter what you do. So if you take a 4x4, you're going to have to break once, and then 2 times, and 3 times, always. So the invariant will be exactly m times n take 1 for this question. And, I mean, that's kind of the way you should see it, right? So, take from that, small chocolate bars with this number of pieces, and then, with 1 piece, 0 breaks, 2 pieces, 1 break, 3 pieces, 2 breaks, and so on, and until you reach the solution, which is m times n take 1. So let's try to do the next one in about 5 minutes. This one is a bit more complicated. And usually I try to have questions similar to this in the exam. So, try to work on this one. All right, so we cut out two opposite cornfields of a chessboard. So a chessboard has, 8 by 8. Is it possible to put 31 domino tiles of size 2 times 1 on the remaining 62 fields of the chessboard? All right, so when you look at a question like this, the first thing you have to do is, I have a 2 by 1 piece. It has to be an even number. I have 62 fields. That's good. So, let's work from here. But then you will start to try to put these pieces into this board, trying to reduce the scale of the problem by, making it 2 by 2, 3 by 3. It will not help you too much. So in this case, you will need to find a different way to solve this question. So hold on a bit. So let's try in the next 3 minutes, so 4 minutes to do it. Yes.
You can't, right?
No, but what?
Because if you colour it like a chessboard would be, or 2 by 2 pieces always have to be one colour's black, one colour's white, and the corners is going to be the same colour, so you can't.
Yep. They're more interesting questions, but yeah. It's hard. So one thing about this question is a bit deceptive because I present a chessboard without the black and white colors. If you have the black and white colors, it may tell you something about the answer.
Because you got in the middle, you got the center, they're both even on both sides. So what's that? 1, 2, 3, 4, 5, 6 even at the bottom, right? And then 8 going up. So that's a middle section. And then those 2 sections on the side, they're odd numbered.
Well, that's good. This is an algorithmic way to explain it. Can you find like a more convincing way?
Okay.
But that's good. I would accept that. Yeah. No, they have to cover the 2 pieces.
But is it like, so you put them, you like line them up until it gets to the one at the end, and then you like one up, and then you move it along to the end. And
Yeah, you can do that. Did you try? Did you try? You can do that. You can try.
I don't.
Okay, so here's the chessboard, and I remove this part, and then I have these domino pieces, right, that I need to put there. And I mean, probably the first thing you tried is to see, okay, so let me just put, this piece here, and then this will cover here, cover there, and so on. And then you can do this until you keep going, right? So, we'll kind of go in these S shapes here. And all of a sudden, you have one piece here that doesn't fit. So maybe I started the wrong way, and then I can start to put these domino pieces in different ways. And in the end, you will find that you will not be able to do it. You know, no matter how you try to put this piece, there's no way you can fit these domino pieces there. And the fact that you have the black and white squares now makes sense, you know, because you can try to answer why you cannot do it, and why is that? So when I remove these two corners, is there something special about these corners? Both black. Okay, and yeah. Yes. Yes. So exactly. Once I remove these two pieces, I'm removing two black fields, right? And what remains is 32 white, 30 black fields, which means that it's impossible to fill this domino, this board with dominoes, because these two numbers, they must be the same. So, you know, if I remove one piece from here, one piece from here, that's fine. I could do it. But if I remove, you know, like, you know, the corners in this way, it wouldn't be fine if I, you know, I kept these two. So they should have, these two numbers here must be equal in order for you to be able to fill in the whole board with domino pieces. There are way more interesting questions than this with, you know, more interesting pieces. But it's important for you to realize that a lot of these questions, they will be proved, you know, right or wrong with something like this when you color the board in some particular way. I will try to, you know, bring some questions like this to you because, you know, every 2 years I have a question like this in the exam. So is that okay? All right, so let's go to the challenge today before we leave. And it's, you know, if you've been paying attention to this class, you're going to figure this out very quickly. Otherwise, you're going to have trouble. All right. I will randomly pick 99 numbers from 1 to 100 and show it on the screen. Without repetition, that is, one number from 1 to 100 will be missing. You cannot answer this question by constructing a table with all numbers from 1 to 100 and see which one is missing. The first one who can tell me which number is missing gets the 1%. But you need to model the problem. You need to tell me what the invariant is. All right, so these are the numbers, and what is the missing number? So here's a hint. You're allowed to use a calculator. You cannot use a table. What is it? Just like I can't hear you. Yes.
You do the n like that.
Yes.
For 1 to 100.
Yeah.
Before, and then if you summed up all of those that are on the board,
Yes.
took the difference between the two, that would be what's
Yeah.
remaining.
Yeah. Yeah. So that's the model. But what is the solution? I need a solution. No, that's the way I was expecting.
Oh, really?
Yeah. If no one gets the answer, I give you the 1%. But I mean, you have the upper hand. Just use it. Yes.
11 is missing.
How? Why? Did you memorize the numbers?
Yeah.
No, there's no mental table, nothing. I want like a solution with a model. It is 11, but how do you get this?
Let's spend time observing.
Just
We
look
do,
and you just
yeah, we do the manual approach.
Yes. Yes. How?
Because there are only 8 numbers up there that are in the tens.
No. No, there's no table. Give
No,
me.
it's in. It was not. It's not so much. It's not so much going through and identifying every number that's there. It's going through it in a pattern so you reduce the amount of numbers that you have to look through. So you eliminate sets of 10 at a time until you get down to a point where you've got real
Yeah,
fewer
but
numbers to check.
this is not the invariance. So the class is about invariance, right? So yes.
I just suck at
Yeah.
Plus to 100 and the minus 1 number.
Yeah. So what is the number?
Minus 1
This is what you
11.
get. So did you get this question by this?
Is 1 plus to the 100 and the minus 1 number.
1
Plus to the
1 plus 100?
1 plus 2 to the 100 and the minus 1 number.
So how did you can you write down? Sorry, I will get to you. Don't worry.
Minus 1 number.
Yeah. So did you sum up the numbers?
It's 11. I just use my eye to find it is 11, but the method will be this.
Yeah, but I want the actual method that you use. So how did you solve it? Yeah. Okay. So did you do this? Yeah. Cool. Good. So can you explain?
You multiply 100 by 101, divide by 2, and then you start minusing every number that's up there until you have what's
Yeah.
left.
Yeah.
It's 11.
Yeah, but he got first. Sorry.
I have my hand up as well.
Uh-huh.
I have my hand up as well. So
Yeah.
I'm going to take a random guess that you add them up and you get 5039.
Okay. All right, so a couple of you got the right model, but only he got the model and the solution. So can you explain? Do you want to, do you remember the numbers or?
So
I don't. Just tell me what you did. Okay. All right.
So we know that the sum of the numbers from 1 to 100 is 5,050. 5,050. And then if you sum all the numbers on the board up, you got. And then if you just take them away from each other, you can find the missing number.
All right. Thank you. Thank you very much. All right. So before we leave, so there's a link here that goes to a YouTube page. This YouTube page has just a fantastic puzzle on invariance. Try to do it. I mean, if you manage to do it, you are in really, really good shape. Okay. So just give it a shot for this.